So in this video we're going to talk about Hilbert spaces and inner product spaces. So as we've seen before, in a norm space we can add vectors and multiply vectors by scalars. Further, norm on such a space generalizes the elementary concept of the length. So let me put it this way. So norm is, I can say, equivalent to my general concept of length. But what do I want in all these abstract spaces? So what I want is an analog of the familiar dot product. So what I mean is, if I have a vector space and I can do this operation and I can define my norm in terms of this inner product, then this would give a very good structure to my space. So I want that even abstract spaces resemble the structure of my Euclidean spaces, because then working with them becomes easier. And we would see in later part of the series that the more structure I have within my spaces, the better it becomes to work with them or do analysis on them. So the fundamental reason I'm looking now from a normed space to an inner product space. And what is the difference between a norm space and an inner product space? Well, an inner product space is also a norm space, but the norm in an inner product space is defined in terms of course, inner product. Now, when I define inner product, I have this condition of orthogonality which comes with it, that A dot B is equals to 0 if A is perpendicular to B. So that's the idea behind defining a new kind of space, which is my inner product space. And let's dive into the dynamics and the mathematical definitions of my inner product space. So start. So again, an inner product space is a vector space X with an inner product defined on it. So with an inner product defined on it. And what is the mathematical definition of this inner product? Well, this inner product is nothing but a mapping from X cross X to the scalar field K of X, or in this context I would rather say to the scalars, scalar field. So an inner product space is also a norm space where the norm of any element X is given like inner product of X into X to the power 1 by 2. And then I have this condition of orthogonality in inner product spaces. And what is this orthogonality? That the inner product of orthogonal elements is equal to 0. And let us see what are the properties of the inner product space. That now, if I have elements, or should I say vectors, X and Y in my inner product space, then these four properties should be satisfied. If you remember about these spaces, when we defined our norm space too, we had these four properties associated with it. That norm of x should be 0 implies x is 0, the triangle inequality, and scalar multiplication, and that the norm is always greater than or equal to 0. So similarly, when we define an inner product space, these are the four properties which vectors belonging to that inner product space must satisfy. Let's look at them one by one. So the inner product of x plus y is a distributive property, as we have seen in around a billion cases before. Now the next property is again that corresponds to the scalar multiplication, that alpha times x with y is nothing but alpha times of x comma y. And then there's this third property of inner product space, which is that inner product of x comma y is equal to the complex conjugate of inner product of y comma x. Now this might seem a bit abstract to you at the moment, but later when I define my complex Banach spaces and complex Hilbert spaces, then I would clear the reason and give more intuition behind this property. But as of now, we have to think of this in this way, that the inner product of x comma y is equal to the complex conjugate. So this sign means complex conjugate. And what was the fourth property? The fourth property was as before, like we had in norm spaces, that the inner product would always be greater than or equal to 0. And last but not the least, that the inner product is 0 if and only if x itself is 0. Just like we had in the case of normed operators. And now an inner product on x defines a norm on x. Again, think of it this way. This inner product defines a norm. So I had a vector space. Okay, I had a vector space. And on this vector space, I had a inner product. And what was this inner product? This inner product was a mapping from x cross x to scalars. And now I take these two things, and based upon these, I say that now with my inner product, I define a norm. With the help of an inner product, the norm is defined. And how is this norm defined? This norm is defined as follows. So the norm of any element is equal to the under root of the inner product of the element with itself. So this is how I get the notion of norm from my inner product. And as we saw in the last few videos, we learned that the norm gave rise to a metric. So the metric was induced by the norm. Metric induced by a norm. I would repeat my point again. The metric induced by a norm essentially mean that I have my norm, I have the notion of my length, and based upon the notion of this length or norm, I give the notion of distance. So similarly in this case, my metric is given via this formula, is equal to this representations. So this makes sense to me. If you compare it with the metric that we defined on our norm space before, you can find several similarities between these formulations and the formulations that we did in the case of norm space. So now it's the time to summarize everything. and give the introduction of the most interesting, beautiful and useful space in all of function analysis, which is Hilbert space. But okay, to summarize. We had an inner product space. What is an inner product space? An inner product space is a vector space such that there is an inner product defined on it. What is this inner product? This inner product is nothing but a mapping from x cross x to the scalar field. And based upon this inner product, based upon this mapping, I get the norm. See? Norm. So based upon this inner product, I deduce the norm. And these were the 4 properties that the inner product has to satisfy. Once I had these, I say that the norm is nothing but the under root of the inner product of the element with itself. And again, I define a metric on this also via this formula. And one of the things to see here is that the inner product space is also a norm space, is also a metric space. How? The inner product gave rise to the norm gave rise to the metric. And now is the time to introduce Hilbert spaces. So what are Hilbert spaces? So Hilbert spaces are nothing but are complete inner product spaces. Inner product spaces. What do I mean by complete inner product spaces? As we saw in the video before, if I take any Cauchy sequence and I take the limit of it, then the quantity that I get, or the element that I get, if it itself belongs to the vector space in consideration, then the vector space is complete. And that is the idea behind Hilbert spaces. Hilbert spaces are very important. All of our formulations in quantum physics would be based on our understanding of Hilbert spaces. If you have any doubt, any comment, any suggestion, I would love to know and improve upon the videos. See you in the next one.